In my new whitepaper series, I will overviewing white papers of impactful cryptocurrencies, which can often be difficult to parse through anyone without an advanced statistics and computer science degree. Today, I will highlight the coin everyone is talking about, Solana. While reading through the 32-page document linked in description, I noted that Solana's white paper is even more technical than most, so please respond with any questions or comments. Thanks again. Don't forget to subscribe and smash that like button like it's Coinbase customer support during a crash. Contents include blockchain architecture, security framework, and finally network vulnerabilities. The Solana team and myself emphasize that the document is not an offer to sell tokens, nor is my video. Introduction to blockchain architecture. Solana introduces a new blockchain architecture designed for high performance and efficient transaction processing. The Solana blockchain's proof of history (POH) concept ensures verification of time passage between events in a trustless manner for enhanced efficiency in processing transactions. Solana highlights the significance of time in blockchain operations and emphasizes the unreliability of clocks in current public blockchains. The POH concept creates a ledger with verifiable time passage and event ordering, without need for trusting external sources of time. This facilitates synchronized decision-making among network participants. Network design and transaction flow. Solana's network design appointments a leader to generate a proof of history sequence to ensure global read consistency and time verification. Verifiers replicate transactions and compute confirmations per the Byzantine fault tolerant, which you are encouraged to review. The system operates optimally even during partitions, leveraging a proof of stake (POS) algorithm for recovery and maintaining control of the network. Time verification through proof of history. Proof of history involves a sequence of computations to verify time passage between events cryptographically. By recording the sequence of outputs of a cryptographic function, Solana ensures that data timestamps reflect actual occurrence times. Horizontal scaling of this process is achieved through synchronizing multiple generators, without resorting to shard-ing methods. Verification and consistency maintenance. Verification of POH sequences can be efficiently carried out with multi-core computation. To maintain consistency and prevent attacks, users are encouraged to enforce sequence integrity by appending the last observed output within each new event they create. This method safeguards against potential malicious intentions and ensures the seamless flow of transactions. Solana's innovative approach to blockchain architecture, leveraging POH and POS algorithms, showcases the potential for high throughput and sub-second finality times. By addressing time verification and scalability challenges, Solana aims to enhance the efficiency and reliability of blockchain networks. Part 2: Blockchain Security Framework. Summary of Proof of History, POH, Sequence and Proof of Stake Consensus. Proof of History, POH, Sequence. Proof of history is a concept that involves using a historical record of events to verify the order and validity of transactions, preventing partial reordering attacks. Each event in the sequence references the hash of the previous event, ensuring integrity. To prevent malicious generators from tampering with events, clients can submit signatures along with event data. The system has measures in place to limit attacks, such as reversal attacks, speed-related attacks, and long-range attacks. The combination of proof of history and proof of replication is designed to defend against forged ledgers. Attacks and defenses. To maintain scope of this video, I again cannot go into much detail, but I recommend all of you to do a bit of research on aforementioned attack strategies. I can refer you to resources if you comment below. Discussed attacks include reversal attacks, speed attacks, long-range attacks, tragedy of commons, collusion with the generator, censorship, and ASIC attacks. Defenses against these attacks are proposed within the POH framework, such as using timeouts, detection mechanisms, and incentives for network participants to maintain integrity. For example, in the case of a tragedy of commons where verifiers may approve every state hash without verifying, introducing occasional invalid hashes can trigger actions to prevent malicious behavior. Proof of stake consensus. Proof of stake, POS, consensus is discussed as a means to confirm the POH sequences generated, select the next POH generator, and punish validators for misbehavior. The process involves bonding coins, voting, unbonding, and electing new POH generators in case of failures. Measures like slashing address issues like nothing at stake problems, where validators might confirm multiple branches simultaneously. The system aims to achieve supermajority consensus for all decisions in the network. Recovery and finality. The recovery process outlined emphasizes the ability to fully recover the ledger from any failure. This is particularly noteworthy to Solana, which has fallen victim to various outages in previous years. Validators can recover from partitions, and the consensus algorithm ensures finality by requiring timely responses from network participants. The POH generator's role in maintaining the stream of messages and validators' responsibility to validate within set timeframes contribute to the network stability and reliability. The white paper details a comprehensive framework that combines proof of history sequences with proof of stake consensus to ensure the integrity, security, and reliability of decentralized networks. By addressing various attacks and implementing defenses, the system provides a robust foundation for transaction validation and network governance. Part 3: Blockchain Network Vulnerabilities. ASIC attacks during finality. Solana highlights a vulnerability in which Byzantine validators with a bonded stake can exploit the network by collaborating with a proof of history (POH) generator to inject votes with the help of an ASIC. However, if the POH generator is also compromised, it can communicate the counter to the Byzantine validators, making the attack similar to sharing identities and hardware among collaborators. Streaming proof of replication. Newly proposed streaming proof of replication algorithms aim to enable fast verification of proof of replication by leveraging a proof of history generated sequence. The algorithm involves encrypting data block by block, generating proofs using specific hashes, and ensuring proof validation through a select number of cores available. The process also involves key rotation and hash selection for enhanced security measures. This is one example that highlights the collaborative nature of Solana's infrastructure, as well as interdependence of technical architecture across crypto projects. Proof validation and attacks. Proof validation entails replicating the state of the blockchain for high availability, targeting a specific replication pattern while ensuring computational, network, and memory limits are considered. Potential attacks discussed include spamming the network with bad proofs, partial erasure attempts, collusion with POH generators, denial of service attacks by creating multiple replicator identities, and the tragedy of commons scenario where validators may confirm POREP without actual verification. System Architecture Overview. As discussed earlier, Solana's system architecture comprises key components like the leader, proof of history generator, state, naive hash table for user addresses, verifiers, nodes ensuring high availability of the blockchain state, and validators, which are virtual nodes consuming bandwidth from verifiers. Network and computational limits, memory constraints, and high-performance smart contracts leveraging eBPF bytecode are discussed to optimize system efficiency and throughput. Technical references. The document provides references to various technical papers and articles related to consensus algorithms, ordering oracles, proof-of-stake mechanisms, and elliptical curve cryptography acceleration using GPU, shedding light on the broader context within which the discussed concepts are situated. In summary, Solana's white paper delves into the intricacies of network security, blockchain replication, system architecture, and potential vulnerabilities and attacks encountered in distributed ledger technologies and consensus mechanisms. The proposed solutions and algorithmic approaches aim to enhance the efficiency, security, and scalability of blockchain networks. Please follow my account for more crypto content, and don't forget to press that like button.